Okay, now things are going to start getting weird. All right. I told you about light in the previous video. I told you how to wavelength and all stuff. Like we know that light is a wave. It behaves like a wave. That is absolutely for certain. But the thing is, the wave nature of light doesn't explain how an object can glow when its temperatures increase. Physicists around early 1900s were really trying to figure out what was going on when you heated up a piece of metal and it started to glow and then heat it up hotter. They were trying to reproduce some stuff that they saw in experiments using math and equations and treating light as a wave. And it worked fine for low frequency stuff, but when it got to higher frequency, it ended up in something they called the ultraviolet catastrophe. It predicted that, once you got something glowing white hot, it would be spitting out infinite amounts of energy and just crazy stuff that wasn't right. And this really caused all sorts of problems and confusion. And along comes a guy named Max Planck. And how he solved this is kind of funny because even he said that it was just kind of a guess. He just kind of went out on a limb and was like, okay, let's just say that energy, instead of just being kind of continuous, like I can add or take away as much energy as I want, that it's only added or subtracted in little chunks, all right, little packets. So energy comes in these little packets, and he called these little packets quanta. So quanta is plural of quantum, as in quantum mechanics. And this is kind of the birth of quantum mechanics. So this crazy idea that energy came in like little nuggets. So it's kind of like the smallest piece of gold you can have is one atom of gold. The smallest piece of carbon I can have would be one atom of carbon. He had this kind of idea that the smallest bit of energy that could be absorbed or released would be one quantum of energy. All right, so quantum of energy, it's the minimum amount of energy that can be gained or lost by an atom. All right. Later on, this helped explain what was going on with the photoelectric effect. And so what that is when you shine a light on a metal surface, you can kick electrons off of that surface. But the deal is that light needs to have a particular frequency. So any frequency that's too small will not eject an electron at all. It doesn't matter how bright you make it. It could be just blinding, the most intense thing. If the frequency is not right, it will not kick off an electron. All right. But once you hit that minimum frequency, an electron will fly off there. And if you go above that frequency, the electrons are kicked off even faster. So the electrons are given even more kinetic energy. So what that made him think of is, okay, if this thing's kicking them off and the more we change the frequency, the more this energy increases on here, that we can say that energy is proportional frequency. So light has energy, and the energy of that light is proportional to the frequency. So remember, that's what this nu is. It's not a V, it's a nu. This H, it's a proportionality constant. It's called Planck's constant. All right, so we have E equals H nu. It's a really important equation. So the energy of light equals Planck's constant times the frequency of that light. All right. And this also it kind of spiraled into another thing. So if energy is coming in little chunks, little nuggets, and we know that light carries energy, light was actually acting like it was in little nuggets, little chunks, little pieces of light. And the smallest piece of light you can have is what we call a photon. So one photon of light will carry one quantum of energy with it. And we can calculate that using this equation. So this is the energy of one photon of light. So one photon of light, we can calculate that energy based on its frequency. So that's kind of cool. So light's a wave, we know that, but it's also acting like it's a particle. So you may have heard wave-particle duality. That's what it's talking about here. And it gets even weirder when we actually start talking about electrons, because electrons, they have matter, but they also have wave properties. It's crazy. But we'll get there when we get there. So really important equations here that you need to know. C equals nu lambda. So C is the speed of light. This is a constant, 3 times 10 to the 8 meters per second. Nu, this is your frequency. All right, frequency is measured in either per second or 1 over second or hertz. Those are all the same units, really. And this upside down looking Y thing, that is lambda. That is your wavelength. So the wavelength should be in meters, right? Because this is in meters per second. This is in hertz. or per second. So if you have meters times per second, it gives you meters per second. That makes sense. And this is the equation that you just learned a second ago. E equals h nu. So E is your energy. This is measured in joules. So joules are a unit of energy. So we have energy in joules equals Planck's constant. That's 6.626 times 10 to the minus 34 joule seconds times the frequency, which is per second. All right. If we do some algebra, and in class I always talk about, like, you can always spot a nerd. Just ask them, hey, what's new? And if they say C over lambda, you found yourself a nerd. Because when you solve this equation for nu, right? So divide both sides by lambda, you get C over lambda equals nu. So I can put that in here and say E equals hc over lambda. So now I can calculate the energy of a photon if I know its wavelength. Cool. All right, so don't forget, how to spot a nerd, ask them what's new, and they'll say C over lambda. All right, another thing here. So you've seen this slide before, but now I just kind of wanted to tack on some stuff, because there's a lot of stuff in this chapter where, like, some stuff's directly proportional, some stuff's inversely proportional, but this kind of spouts it out all nice and swell. So if you just remember, long wavelength, that means it's low frequency, low energy. If it's short wavelength, that's high frequency, high energy. So think of the kind of light that's bad for you, right? Ultraviolet, X-rays, those things, they don't like shooting you with those things a lot because you're going to get cancer, right? Those have enough energy to break bonds. And when cells have bonds broken and sometimes they screw up and they don't kill themselves off, then you get them replicating themselves and they're all mutated. That's no good for you, right? No bueno. All right, let's keep on going. Let's keep on going with this chapter. All right, so another weird thing is that they saw was that atoms and molecules, when they gave off light, it wasn't quite normal light. Like, if you just look at it with your eye, like a neon tube, it looks fine. It looks like light. Sure, you can even light up a pickle. Unusual, but yeah, it's light. But if you were to take this light and shine it through a prism, it's going to be different than sunlight. It's going to look a lot different than sunlight. All right, so with sunlight, you're going to see a continuous spectrum. You're going to get that full rainbow. But when you use an atom or like a molecule, right, you get what's called the line spectrum. So if you look at the emission spectrum of sodium, you just see these two lines. Like, this whole thing is gone. You're only seeing two little stripes that are right here in the yellow. When you look at hydrogen, there's only 4 lines you see. Right, here's hydrogen again. Here's neon, a whole bunch of little lines. Let's focus on hydrogen, because this is like what's really going to get us into quantum theory here. So hydrogen always gives off these 4 lines. Right? There's a red line, there's a green line, a blue line, and a purple line. We can measure those wavelengths. All right, so we know the wavelength of those things, and if I know the wavelength, remember a couple slides back, I just showed you an equation that allows us to calculate energy. Right? E equals hc over lambda. So what that means is that the hydrogen atom is giving off these lines of color, and each one corresponds to a very particular energy. What's going on? All right, so what the heck is light, actually? I'm going to tell you. So light, when an electron goes from a high energy down to a low energy, it releases the difference as a photon of light. And also it works the other way around. If you shine light onto an atom, if you shine the right frequency or the right wavelength, the right energy of light, you can take an electron from a low energy state and pop it up to a higher energy state, so it'll absorb the light. But when electrons move from high energy down to lower energy, they release that energy difference as a photon, and that's what we see as light. So when we see these 4 lines in the hydrogen spectrum, these are from different transitions in that atom of electrons moving from different energy levels. So this is telling us that there are energy levels inside the atom. So it's kind of like this guy on the ladder here, right? You can't levitate or hover in between the rungs. So like, I can stand here or here or here, but nothing in between. Electrons are kind of the same way. They have certain energies. They can be at this energy level or they can be at this next energy level, but they're not going to be anywhere in between. And that's where I want to stop, because I'm going to get into like the whole Bohr model of the atom for the next chapter, or sorry, the next lecture, the next video. All right, I will see you then. Right on.